Copper oxide nanomaterials are widely used in industrial applications such as boat paints and can be inadvertently introduced into estuarine and marine environments. Copper is a toxic metal and has known negative effects on marine life. Cristina Torres-Duarte, a postdoctoral researcher at the UC Davis Bodega Marine Laboratory, is currently studying the potential effects of these copper nanomaterials.
So copper oxide nanomaterials are used in antifouling paints because they can slow the growth of organisms that can attach to boats and can affect performance. Copper oxide nanomaterials are used because they can slowly release copper ions into the water and prevent fouling for longer periods of time as compared to soluble copper. The problem is that these nanoparticles can be introduced into the environment because they can peel off from the boats, or simply they can leach out of the paints. We are concerned about these materials because we know copper is highly toxic. It can interfere with many biological processes. And now we want to know if copper in a nanoform will be more persistent in the environment, or if it will have toxicity related to its nanoform. The toxicity of copper oxide nanomaterials has been previously studied, but there are not that many studies that have focused on the mechanisms, and that was the motivation behind my latest project, where I studied the developmental effects of copper oxide nanomaterials in sea urchin embryos. We selected sea urchins as a model system focusing on early developmental stages when exposure to chemicals can have major impacts on their morphologies, development, and survival as larvae. We also studied the effects of soluble copper and two different copper oxide nanoparticles, ones that were synthesized in the laboratory and ones that are commercially available. The synthesized nanoparticles have a smaller size, a smaller range of sizes, and they are more stable in the water column, as compared to the commercial nanoparticles that have some impurities, have a wider range of sizes, and they can sediment faster in seawater. The reason why I selected two different nanoparticles is because we want to know what properties affect their toxicity. So in this study, we discovered that copper is toxic in sea urchin embryos because it can affect the development of the skeleton when it's present at low concentrations. But as concentrations get higher, about 50 micrograms per liter that can be found in heavily polluted marinas, the effects are very dramatic. They don't develop a skeleton and their gut is very malformed, which in turn can affect their survival and can eventually lead to their death because they won't be able to feed during their larval stage. The morphologies that you can observe when they are exposed to soluble copper are very similar to the ones that you observe when they are exposed to nanocopper. However, the concentrations at which these effects can be observed are quite different. The synthesized nanoparticles are 10 times less toxic as compared to soluble copper, while commercial nanoparticles are 100 times less toxic than soluble copper. These differences in toxicity are mainly due to solubility. The synthesized nanoparticles can dissolve faster, meaning that they release more copper ions into the water, while the commercial nanoparticles dissolve slower and they release about 0.1% of the total copper into the water column. It might seem like good news that the commercial nanoparticles are less toxic. However, they can accumulate as nanoparticles inside the embryos, and since they dissolve slower, they can have longer lasting effects inside the embryo. What we want to understand next is if these effects caused by copper oxide nanomaterials are reversible or not. What will happen if the source of pollution is eliminated? Can the organisms recover or not? So I've been working on this, trying to determine what developmental stages are more sensitive to exposure, and if a specific stage, if you eliminate the source of pollution, if the organisms can actually recover. Another project that I'm working here at BML, together with the Bodega Ocean Acidification Research Group, is understanding the interactive effects of copper oxide nanomaterials on their ocean acidification conditions. The acidification of the ocean is a reality because as we have increased the concentrations of CO2 in the atmosphere, the pH of the ocean is decreasing. And as the pH is lower in the ocean, the behavior of the nanoparticles can dramatically change because it can increase their solubility and increasing their bioavailability and their toxicity. By understanding the combined stressors together, we can raise even more awareness into the public of how pollution is affecting wildlife as well, and it will eventually affect humans as well.